responded to run here.
Okay. So anyway, if the data is so large and then so so anyway, what people can do is pretty similar, and then so depending on the different fields, but yeah. So another approach is like a local GP. The local GP is very crude, but practically this is really working very good. Its basic idea is that you partition the data into the m small group.
This is what we call clustering approach.
Clustering approach.
It also corresponds to what we
Okay. Yeah. Just feed the independent model for each data group. Okay. So here is actually the data group size is the B, which means that each group you have the B number of the data points. Computation is reduced. Okay. And then so also is the parallel computing can be done because each model is independent, and each model can be run independently. So that's actually the local GPs. There are some approach, and then so different versions. Some version is do not use the data partitioning. They are kind of using some soft partitioning. So depending on the testing locations, and then so given the testing point, they find some neighborhood. So like for example, in the k-nearest neighborhood, and they're using only the k-nearest neighborhood for the predictions. That's the one approach. But the more popular approach is just at the beginning in the training stage, they just hardly the data and they just learn. Okay. So this is the more computationally efficient because the first approach I mentioned is the kind of expensive if the testing point is so large. Okay. But yeah. So anyway, the local GP means just learning local models. So this local model has some issues. For example, if you have independent models, and then typically you partition the data depending on your X locations, right? Because if your data along to the neighborhood of some certain region, and they are correlated, and then so partitioning along to the data input location is the more natural because they are more correlated each other within the groups. Okay. So then if you learn actually the one models for each sub-region of your regressions, okay, then your prediction is pretty much has some problem at the boundary of the two local regions. Okay. So prediction, you have the two different points. So that's natural because those are independently learned. Predictions are different because they are using the different training data. Okay. So then the prediction at the boundaries that you have a two, which one you need to choose, that's the ambiguous. Okay. So this is just a very simple example in the one dimensional, but if you have a high dimensional, so you have the more than the d number of the prediction from the neighboring local regions. Okay. And then so high dimensional, this is the much the worse. Okay. But then even in the 1D, so you have the larger problem, it's the mismatch. And that mismatch is not just the aesthetic problem of your regression functions. So you have some prediction accuracy is significantly worse around the boundary of the local regions. Okay? That actually happens in the many regression setting, right? Because along to the boundary of your local the region of the regressions, you do not have any much training data set compared to the center of the regions, right? So then you use the less number of data points, your prediction is worse than the center. So if you partition, you have the more boundaries, and then your prediction is the worse along the boundary. Okay. If you have one more partition, probably it's getting worse. Okay. So this is the so-called the conflict of the multiple prediction problems. Okay, you have the multiple predictor at the same point. Okay, so that prediction is not very accurate because of the boundary issue. Okay. So then the possible mitigation of this issue is taking the mixture of the local model. Okay, and then so lots of the ensemble approach is proposed. So first thing is the Bayesian committee machine, and then so bagging, dirichlet process mixture, Bayesian model averaging. And anyways, those are like ensemble technique is the pretty general technique, and they just borrowed this idea of the ensemble learning technique in combining the local GP predictors for making some weighted average of the local GP prediction. Then you have some one single prediction. So this one is actually a pretty good approach for solving the problems, but the computation side, and then so this taking the mixture is not very good because anyway you need to evaluate all the local GP predictions for making some one prediction, and then even though many of them is the very small weights, okay? And then so that's actually some computation issue with this approach. So our approach is our focus of this talk is can we do some other way of doing solve like a conflict of the predictor issues. Okay, that's actually the major topic of this presentations. Okay, so which is so-called we are kind of so-called the patchwork cleaning is because we are patching the local piece into the more continuous way. So let me explain the issue, and after that is I explain how we address this issue. Okay. So conflict of the multiple prediction issue is we have the partition of the data in the local GP. Suppose we have the input domain of the regression function is the partition into the k local pieces. Okay. So each piece of the input space is the so-called omega k. Okay. And we actually in the local GP, what we actually do is we learn the one regression function as an approximation of that local region. Okay, that is so-called the fk of x. Okay, so each local GP is the kind of learning this local approximation. Okay, and then with some prior, which is the same prior as the original problem, and but only using the local data. So then, this is the kind of illustration of the partition. If you have a two-dimensional data set, this is the first dimension of the x, this is the second dimension of the x. If you have something rectangular domain of the functions, you can partition to this way along to this boundary, and then you have the one data set here, the other data set here. So you have the one prediction, and then so you have the another prediction. You have some problem in the conflict of the prediction along to this boundary. Okay. So then, it's the primary problem is what I just mentioned is the prediction of the two local piece does not consistent in along to this boundary of the two neighboring local region. Okay? So that happens, and then all the boundaries, internal boundaries within the partitioning. Okay. So then, what we're trying to do, how we combine the two pieces together, is we kind of proposed another prior, which is the so-called patchwork prior. Okay. So we define the auxiliary stochastic process, which is defined by the difference of the two local pieces. Okay. So you remember in these two local pieces, the local Gaussian process. Okay. So with the same prior. And then so we take the difference of this stochastic process along to this boundary. The auxiliary process only defined on this boundary. Okay. So then as you can see, as a priori, we already know that this difference should be equal to 0 in order to make these two local pieces continuously connected, right? So that's the prior information. We call this prior information as the patchwork prior. Okay. So then what we do is actually so we are actually using that prior incorporate into the Bayesian frameworks. Okay, so we actually exactly same as the local GP. We partition the data, define the local approximation, and then each approximation is we estimate jointly under the prior and the local data. Okay. So we have each local piece is the Gaussian process same, okay, but those are independent. Okay, each other, mutually independent each other. So local piece is just independent. Okay, but we have the second layer of the prior, which is the difference of the local pieces, and then that should be equal to 0. Okay, each pair of the neighboring local region. Okay, that is the patchwork prior. Okay, so we have two priors, and then so we have the local data, and then so each local data is only utilized by each local piece, and then so if this setting is given, and that's how we learn the actually prediction. That making some more actually continuous prediction in the posterior, because the prior is we have the same predictions. So then this is the forcing. Actually, the older prediction is the continuous.
So if I don't use a prior, but just add this set of equality constraint, like just in the spline setting, we can still continue the computation.
But that is really.
It's difficult to come up with a prior satisfying. I mean, it's probably not that difficult to you. But I'm just saying, actually, you can directly solve the problem with this set of quality constraints. I mean, just like in the spline setting, right? I mean, we have the continuity maybe to the second.
Right.
I mean, to the first order.
Right. So spline is this is very similar to the spline, right? And then, but the difference is like the spline is you have the local basis function, right? And then so support is the spline basis, typically locally based, and each basis is actually kind of the local approximation of around that neighborhood. right? And it's you're putting all the spline together, and then for making some, you have the consistency, right? And then also some more the smoothness around actually the connections, right? And then, but this is the more like a group-wise spline, because we not having spline within each block, within the local blocks. So we are just putting the two local blocks together, like a spline. So this is somewhat similar to the more like group-wise splines. But so nobody done that in that group-wise spline, right?
But what I said actually is, I mean, after impose those additional constraints, I mean, actually in splines, those basic functions are global. It's just because they're like the derivation results after impose these equality constraints. Of course, I mean, some parts are zero, but it's actually going to be a global function. I mean,
right, the global function, yeah, but actually those are locally correlated each other, the basis, right?
So I'm wondering if I put these additional constraints and then derive this thing, maybe this can result in some natural results. I mean, natural, this FKs.
So I believe if you are using the spline basis, that is the more like it's like a Gaussian Markov random field. Because you have it's a correlation in the local.
But we can still use the divide and conquer approach. We can actually split it. I don't think actually it's that. I mean, locally, of course, it is.
Right.
I'm just wondering what the results would be after you use actually local, things with this equality constraints, these continuity constraints.
Yeah, I believe that's the one possible approach, and I believe that's pretty similar to the Gaussian Markov random field approach, because the covariance matrix is pretty like spline is a correlation is like a Gaussian Markov random field, right? And
locally.
Yeah, locally correlated is only, right? And then
But now your problem boils down how to design the splines, right? I mean, satisfying.
Yeah, exactly. And then also it's the spline is if you specify the spline basis, your covariance function is constructed from your spline basis, and that's the totally different problem. This is the kind of approximating.
That's why I asked what would be the results be, in fact, if I assume the model and then add the constraint. I believe actually it's still doable, but
I believe the practical sense is pretty similar.
I don't want to design something from my head and then apply to the problem. Actually, I'm asking in this framework, after adding the simple equality constraint, what would you count?
Yeah, the practical sense is I believe it's pretty similar, because anyway in the Gaussian process you need to specify what is the covariance function. It's the kind of choosing the similar to the choosing the spline basis, which is spline basis, right? In the B spline or some other spline. And then, but anyway, they're pretty similar. But so this problem is starting with given the covariance and how we approximate. And the spline is the kind of constructing the covariance field if you're choosing the spline, right? And so anyway, the problem, but the practical sense is I believe is pretty similar, and that they have some similar result. So anyway, this is the two-level priors, and then we assume, and then so based on that is we try to estimate. So then the only issue is that is the delta KL auxiliary process is the Gaussian process. Okay, that's the stochastic process. Okay, defined on the boundary. Okay. And then mean function of the auxiliary process is the 0. Okay, if the f is the 0 mean, and then but still is the not 0, and then so still is the same, because mean function of these two is the same on the boundary. That is that is the 0 mean function. Okay, and then it's kind of makes sense because difference should be around 0, right? And then but the covariance is like a double of the original covariance function. So you can easily divide this. Okay, and then so just using the property of the covariance. And then definition of the delta, you can have this. Then the problem of the delta is the stochastic, is how you force your stochastic process is equal to 0, and so that's it's more like a issue, right? And then so what we suggest is we introduce some the pseudo observation of this auxiliary process, okay? And then so suppose we have some boundary along to your internal boundary. Okay, you place some pseudo observations uniformly along to the boundary. Okay, so then that observation is going to be 0 because the difference is going to be 0. That's the kind of prior information. Okay, if you put that pseudo observations, so delta stochastic process is the kind of converge to the 0 process. Okay. So because of the smoothness of the covariance, and then also you have some the zero observation, noiseless. Okay? For example, if you put the 10 pseudo observation along to the boundary, okay, so originally you have the like purely random Gaussian process as a prior, but if you put some 10 pseudo observation, that is something like this, okay. But if you putting the more pseudo observation, variance is reduced, and then so mean is the always zero. That is the closer to the zero process, okay. So then what we do is the kind of the using some pseudo observation is the populated over this boundary and to approximate the zero stochastic process there. Okay? So then is our yes.
So by adding pseudo data, actually we are kind of putting constraint that this delta should be there, right?
Yes. But the good thing is even though you put in some finite number of the points, you put some constraint, you do not have any guarantees that your difference is going to be zero. Yeah. But the good thing in the Gaussian is that we have the correlations, right? And if you have a correlations, so something in the middle should be very close to zero. And the variance is getting smaller if you are putting more observation.
So do you want to put the observation at along boundary line? Or
yeah, along just the boundary. Yeah, exactly on the boundary.
Exactly on the boundary.
Yeah. So because this auxiliary process is only defined on the boundary, so observation exactly.
Yeah, I understand, but I'm just thinking about maybe if you allow for extent to let it move, maybe you can even get better results. Because the artifacts here are actually pretty clear. I mean, if you put this at exactly the boundary point. Anyway, we can talk about this.
Okay, sure, yeah. So then the approximate the patchwork reading is we are actually GB prior, and we have definition of the auxiliary process. We have the pseudo data from the auxiliary, and then that's the actually delta, and then we have some local data for this prior. So the overall correlation of the model is like this. Okay? You have the two local models. These two, so your auxiliary process is depending on these two local models at the boundary. Okay? And then so you are learning this local model independently with the local data, but you have some also pseudo data about this auxiliary process. Okay? Without this pseudo data, okay, and then these two are independent, unconditionally independent. Okay? But if you have a pseudo data, this is not anymore the independent. Okay? So given this is so-called the V structure in the Bayesian network, right? And then so given V network, and then you have an observation here. These two are correlated. Okay, condition on this is the observed. Okay. So then now it's actually this pseudo data is kind of linking the two independent local model through this pseudo observation. Okay. So that's actually the kind of how we interpret this patchwork reading. So then you can use the prior and then data you can have the joint distribution given some your prediction points, and then you have the real data and then your pseudo data. Okay. So here's the joint distribution is having some very sparse covariance metrics because you have the properties given some priors. Okay. For example, so each local model actually have some covariance is this is the original sample covariance matrix. But now we have independence blockwise. This is the block diagonal matrix. Okay. So you have the independent models. Okay. But here, so you have some correlation in between the local and then is the pseudo data. Okay. So there is each pseudo data and the local data. You have some correlation unless you have the the local model is the neighboring to the boundary. Okay. This boundary is the boundary of this local model, and then that is actually this condition implies if this satisfies, and you have some non-zero value. But otherwise, this is all the zero values. Okay? And also, it's along to all the pseudo data, you have some correlations depending on the location of the pseudo data. If the boundary is shared by the two same local models, you have the non-zero covariance along to the pseudo data, but otherwise all zero. So then this sample covariance matrix is going to be very sparse. This is a block diagonal, and this is a sparse. Okay?
Question. So
yes.
How many? I think the number of pseudo data is also grow exponentially with dimension, right? Because
that is I explain later. Okay, and then that computation complexity is I explain later.
So how do you control the extent of adding these observations?
So what we observe is actually the number of the pseudo data is not necessarily is the very large. Is because of the smoothness of the covariance. Sure, it's depending on the case, but typically if you assume is that your covariance field is the smooth, you do not much need actually the pseudo data. So because the small number of the pseudo data is the kind of the very good approximations. So anyway, I give some explain some later with some complexity. So this is actually the by conditioning formula. We have the posterior mean and the posterior variance. Okay, and then, so this can be easily computable. But because the major part of the computation of this large convergence. Okay, so this is the n times n the convergence. But this is the different from the original, the sample covariance matrix, because that's the very sparse. Okay. So the complexity wise, and then so anyway, this is you can use some matrix identity, the formula. You can convert this inversion to this form, and then so major computation is comes from the inversion of this n by n matrix, and then so this inversions. Okay. So but this. So n by n matrix is this is a block diagonal. Okay. So the block size is the capital B, and then so k is the number of the blocks. Okay. Then is the matrix is the computation for the inversion is just the complexity is like this. Okay. And also this is the actually it's the large matrix. If you have many number of actually it's a kind of confusing. So this is the should be m. Okay. This is the kind of the typo. Okay. So block size is the m, capital M. So this is the km's Q. Okay. And then this is the related with the so matrix from the pseudo data is this size of the matrix is the number of the total pseudo data times number of pseudo data. Okay. So then that is the proportional to the dimension and then number of the pseudo data per boundary. Okay. So because your boundary number is the increase in the d cube, okay, and then is proportionally to the d, and then so you have the d is here. Okay. So there's the number of boundaries increasing, and then so you have the number of the pseudo data per boundary is the capital D. Okay. So anyway, all the complexity is this, but the good thing is that actually this matrix is still is very sparse. Okay, it's a very sparse. It's the banded matrix, and the actual computation is much less than what I described here. But this is the worst case. Actually, the complexity. Okay.
Just a comment actually. We have seen a lot of situations with like matrix inversion involved. I mean, for large matrices, and usually you want to say do some low rank, do some divide and conquer, so that you can use matrix inversion formula. This is just general scheme. This has something to do with the independence assumption earlier.
Yes, yes. So it's more like so conditionally dependent, but unconditionally.
Just short complement, actually. Yes, in the short complement form.
So it's also the good thing is that this one has the maximum likelihood is in the closed form. It's unlike my previous version, and we can learn the hyperparameter of the covariance functions. It's using some maximum likelihood estimations. Okay? And then so this is the form of the maximum likelihood. So then how we partition the data is the better. That's actually the kind of related with the performance of the approach. Okay. So the basically initial idea is to use just the simple uniform grid partitioning. Okay. But we realized this grid partitioning does not very work well if the data distribution is not rectangular. Okay. The sure is that you can use some triangular boundaries for the uniform partitioning, but so that is also hard for this complex shape of the data distributions. So what we did is actually more like a dyadic, the bisections, like like the trees, okay. And then so we bisecting the data recursively and along to the PCA directions. Okay. So reason why is that we choose the PCA direction is that we try to minimize the region of the boundary. Okay. So if you have a distribution is along to this longest line, and if you partition the perpendicular to this these PCA directions, and then so the boundary region is the less than this line, right? And then so then you have the less boundary region. You do not need much number of the pseudo data. Okay, so kind of minimizing the number of pseudo data. So if that is applied for this pattern, and then so this is the kind of example. So what we do is we bisecting recursively along to the PCA dimension, given some local data after partition.
So I do see a need of deriving say natural cubic splines. I mean, an extension in the setup. I mean, the rigid way of partitioning really causes a lot of trouble, especially after you add pseudo observations. It would rather be done in an adaptive way. Yeah, okay.
Yeah, surely this partition can be combined, but that is the cost of computation always, right? And then so learning the all together is always expensive.
I don't want to learn. I want just on each individual one. Just like natural cubic splines.
Okay.
I mean that involves what I asked earlier.
Okay.
Just adding the constraint will lead it to that.
Okay. So our previous approach is adding the constraint at the beginning, but that causing some problem because how you combine the deterministic prior is like all zero difference, and then combined with some stochastic, and then so you do not have any much the probability model easily derived from there. And that's so this is more the natural combination in the stochastic setting. So anyway, we have some examples, okay, and this is the very simplistic example in the 1D, and then so we have some exponential covariance, and then so noise variance is the one. So we sample the data. This is the actually output. Okay. So this is the cost is all the training data, okay, and then so we have some local GP is the making predictions, and then like blue lines, okay. This is just the mean predictions. And then so patchwork creating is if you apply, and then so you have some continuous, but still is some smoothness is the kind of broken, and then so we are kind of thinking about how we making some smoother the linking. But anyways, this is kind of the linking the local piece more smoothly.
Exactly, I see another point actually over there. So that's why I said actually, sorry, the continuity thing actually is not only on the mean. If you add actually the covariance connection, I mean, you can probably derive something.
Okay.
I mean, I see actually 2 points, pretty obvious, right? Yeah, I mean, the mean is
this,
one.
right? And then
Then it's 3. I see actually the invalid point there.
so yeah.
I mean, just the valid point. I mean, this is pretty obvious, right?
Okay, right.
Theoretical, ideally should.
If that is the smoothest, maybe we have the better predictions.
Yeah, exactly. Yeah, you can increase the efficiency, the sample efficiency a lot, and by making use of neighboring observations.
Right. Yes.
That means the first order, mean connection is not really enough.
Yeah, that is actually the one way of doing that is this. Okay, so you think is that we have the patchwork creating prior here, right? So that is the difference of the functions equal to 0, right?
Yes.
And but if we add one more prior, which is the difference is the first derivative is the equal to 0, right?
Exactly.
So then we have the more smoother. If we have put the second derivative, we have the much more smoother, right?
Yeah. But then you have to design another
Right. But only the
pseudo-
problem is the pseudo data is the increasing. Yeah, right. But that increasing is not the exponential, still is the linear, because if you have one more layer, then it's
Well, it still depends on how partition the data. If
Right. So anyway, we have the very still is the high number of the pseudo data already. If the total number of pseudo data is is the capital B, right? Then it's if you have the one more layer, just the two multiple, and then so it's not exponential increase anyway, but it's just 2 times increase, 3 times increase. So anyway, that is we actually discuss in the paper, but we haven't implement that ideas. So because the computation is the issue, but if you put in the more sophisticated things, and so computation is getting worse. So this is the one toy example, and the second toy example, and so in the 2D example, the exactly same covariance, but in the 2D input domain. So what you do is you partition the data into the 128 domains, okay? And then we cut the one internal domain through this line. That's the first partition we made in the bisections. Okay.
So the different colors mean different.
Yeah, different
magnitude?
color means different the domain. Okay. So this is the one domain. This is the second domain. I just use the color for